Hello everyone and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker's developed to help scientists discover the world around us. In today's episode we're going to talk about X-ray fluorescence, specifically in the mining industry. So X-ray fluorescence and other analytical technologies are very important for maximizing yield, and of course that leads to the maximum profit that you can get, especially in today's world where we're looking at squeezing every little bit out of every site that we can. Now, to learn a little bit more on how we actually apply these techniques, how do we do XRF on some of these different materials, we're going to see it live in the lab. So with that, we're going to head on over. Good morning, Julia.
Good morning, John.
All right, thanks for joining us. So today we are joined by Julia Settlemyer, and she is one of our experts in X-ray fluorescence. And also we are joined by a tiger.
Yes, that's right.
All right. So cats, that's what we name all of the XRF machines, huh?
I think so. Yeah. I mean, I think it's good. It's kind of sophisticated, shows power. I like it.
Yeah.
It's also very personable, right?
That's true.
I mean, if you say it's the XY blah, 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 nobody knows what you mean, but the tiger,
right,
you know.
Right. Hey, did you get the result from the tiger? That sounds a lot cooler than, did you get it from the X3592, right? Yeah. Okay. So speaking of the different cats, so how does this differ from the other machines that we've seen? Because I've seen these bench tops. We've had them actually right here. Yep. Jaguars and Pumas and all this stuff. How's the tiger different?
Well, the tiger is a WDXRF system, right? So that means here we actually use the same principle that you're using in XRD. We use Bragg's law. So we have crystals in there that help us diffract the X-rays from the samples into a certain angle, and so from there we know what elements are in there, and from the intensity we know how much is in there. That being said, if we have an EDXRF system, the resolution depends on how good your detector is. And there's like, the best detectors have so and so many channels, and that's where you are. With these, you can add different crystals and thereby increase your resolution. You can like bring out certain elements more if needed. You can add a collimator that makes the peaks sharper, and it has higher power. So you can also measure light elements. All right,
so ED, energy dispersive.
Correct.
So we have fancy detector, that's going to separate the colors out.
Yeah.
WD, wavelength dispersive.
Correct.
So we have the main energy comes into the sample, hits it, sample glows. Glow
goes to a crystal.
Glow hits a crystal.
Yep.
Crystal is scanned.
Yep.
Gives us our signal.
So basically, if it hits the crystal, then you can imagine it like being the prism on the Pink Floyd album. And then you have your detector that goes around and picks up all the colors, X-ray colors.
All right. And because of that, we get better limits of detection.
Yes.
Better repeatability, things like that.
Yes. So for example, the precision of this one is up to 0.05% relative.
All right. So when do you use different techniques?
It depends on where you are in your mining journey, what your objective is, right? So Bruker has a whole portfolio to help you with. If you're just exploring, you might use a handheld, because why would you take this with you? Right?
Yeah, I've seen those a lot. Especially, you know, you see them on TV shows and stuff, people just walk up, pull a trigger, and yeah, this is this.
Right. If you have a lab that's like close to your mine and you really need rapid results and you need something that doesn't take a lot of time but gives you the whole spectrum, you might use an EDXRF system like our S2 Puma. That can also be brought closer, right? Because it doesn't need that much infrastructure. Although this one is in the studio because we also have a new detector that lets it run without countergas that needs to be pumped in. Which
so
is
what does
cool.
this thing need then?
Right now it just needs higher power outlet, like your D8s.
Okay, so the 208 volts.
Yeah.
That's what it needs.
Yes.
Okay.
But other than that, right now it doesn't need anything else. If you wanted to measure maybe wastewater or powders, you would need a helium connection. But for today in the lab, we're just going to do vacuum measurements, and that's all that it needs. So it's right here, nothing else connected.
Yep.
Only power.
All right, so this would be kind of that, then this instrument, this is going to give us the best quantification.
Correct. So
that's possible.
Going back to your question, what do you want to do with XRF in mining, right? As I said, there's kind of the qualitative information, and then there's, so to know what's actually there, and then there's a quantitative information, how much of it is there. And then the gray area in between, kind of show me what's there, and then a little bit of how much is there. And depending on what system you have, that information gets better or worse.
Okay.
So with this system, it's kind of top of the line. It can give you a very good result of your ores or your precious metals or whatever your elements of interest are in your sample if you set up a custom calibration. And we can also help with setting up these calibrations. But it also has a really powerful standardless program. So if you get something from, let's say you have a mine and either something goes wrong, you take something from the place where something went wrong, maybe you had crud on a pipe, you can put it in there and it tells you what it is. Or you look at a different site, you can bring it there, run it as a powder or as a pellet, and then you will know what's in it and also approximately how much is in it. And to a very, very good precision.
So like you said, it's about get the right tool for the right job that you're doing.
Yes. I mean, if you ask me, I would always go with the SI Tiger because it's my favorite system.
Yeah.
But I do understand that not every mining site is already set up and running like 24/7. Smaller sites, or even if you need a backup, a benchtop is fine.
Okay.
And then again, if you want to see exactly what is in your sample, if you want to explore if you look at a core, or a rock in general, if you want to explore what these like traces are in there, we also have mapping systems where you can do an EDXRF map off it, right? Looks really beautiful.
Yeah. But you even have a version of the Tiger that can do some mapping, right?
It can.
Okay.
Yes. Takes a little longer, but it's WDXRF mapping, and it also makes beautiful pictures. But if you want to measure like the average of what you have, then crush it, put it in there, and then you get a really good average of what's in your mining site.
All right. So now you had mentioned standards.
Yes.
You said Standardless program, things like that. So you generally in XRF, when you start to get in that quantitative side of it, you're going to start using standards, creating calibrations, and I think you've brought some things here today.
Yes, I did bring some standards just to give you an idea what they look like.
Yeah.
Because you come from XRD, you don't know what standards look like. You have like one powder and that's it.
We use a standard to normally check the performance of the instrument, not necessarily to calibrate. There are some calibration methods in XRD too. So. No,
but I brought, so just to give you an overview, so this one is, I think it's a rare earth standard from an Australian company. This one is a NIST standard, that's coal. I do have a reference material from, so that's an NCSDC, that's a phosphate rock from a Chinese source. I think this is Czech, that's an iron ore. This is a European, it even says it in German, it's a European iron ore, so quite a few in another rare earth. And then if you prepare them, I also brought a little bit of that. Actually, I didn't bring that much, but I brought, like, we do have these binders that either come as pre-weighed out tablets. So you mix them in with a weighted amount of your material, and then it kind of grinds it up in between. And then if you press it, right, you get like one of these really beautiful pressed pellets. Or you can buy the binder as powder. And depending on how sophisticated you are, right, you could already have an automation setup that does all of that for you. We even have automation setups that automate fusion for you, where it mixes a little bit of material with a lot of flux that gets heated up and makes a glass disc. So just to give you an idea, right?
All right, so you talked a little there about sample prep, because you don't just necessarily take this, put it in the machine. You have to.
You can do that.
You can.
Yeah.
Okay.
Like so, this one here is a powder cup. I open it. So, right there's powder in it.
Okay.
I think you can see it a little bit. It's like filled up to here, and you can put this in there. But we all know. You might pour it from up here, I might go down here, then I tap it, you don't, right? There is a lot more variation in how dense the sample is. Whereas if I use a press to do this, right, then my operator error gets smaller. Operator error. And if you automate it, like that's totally eliminated, right? Then you don't even have the weighing out error, for example.
All right, so you would so the simplest, you're going to just pour some powder into the little tube. A little bit more is you take it, now you weigh the powder, put it in the standard little cup thing, press.
Correct.
And then the most complicated method would be this flux method?
I mean, it's not complicated. It just takes a little longer and it has a little bit of a higher cost because of the fusion. And it does have different advantages and disadvantages. So if you fuse something, you really want to have high accuracy for for your majors and minors. It's not so good for trace analysis, right? Because your dilution factor is much larger. You do 1 to 10 versus, so 1 gram of sample, 10 grams of flux, or plus or minus something.
Okay.
Whereas with a pressed pellet, you have the majority of it is samples. So you do something like, here I did 7 grams of sample and 1 gram of binder. But you do get rid of the mineralogical effects, and you do get rid of grain size issues, right?
Okay.
So that's very good for your light elements.
So, and then to create the calibration curve, do you just mix different amounts of this powder in, or?
No, that would be not so good, because then you train your system to just always see the same ratio between the elements. So we want randomized, independent concentrations.
So is there a kit available then?
Yes, there is. So we do have, well, yes and no. If you want our kit, our turnkey solution, that comes with a sample preparation, it comes with the standards, and it comes with how you set up the measurements. But we also do support our customers very much by with setting up calibrations. Our goal is, though, that you own your calibration, right? So we help you here and there, but we also want to make sure that you understand what you're doing and you have full control over it. I can also show you some spectra if you want to.
Yeah, that'd be great. With the different prep methods?
Yeah, let's do that.
Let's take a look.
So I'm gonna find it first, and then I think we can switch to my computer. Because my computer, my desktop is a little bit like my desk. So it might be a little not so organized. Let's start maybe with this one here. Speed, loose powder. Okay, now we can show it. So this is very green. I'm going to change the colors a little bit so that we see that. So the blue one is my fuse bead. That's why it says FB.
Okay.
Why is it so high here? Because this is my Compton peak, right? The Compton peak is very susceptible to the overall Z number or atomic number of the samples. So the lighter my matrix is, the higher the Compton peak is, which is also very interesting in terms of using it as an internal standard. But that's going a little bit too far off topic. And then what I have here, this one, the red one, that's my powder. Sorry, I wanted to rename it. Right, the red one is the powder. It says LP, loose powder. And then the green one, because I like it best, and green is gold. That's the pressed pellet. And so if we look here, so one thing we see is this blue one has one peak that the others don't have. That's bromide, because I used lithium bromide as a wetting agent. So that's important to get the fusion disk out of the mold. But other than that, you can see all of the peaks are at the same position. But what you also can see is that the green one is always the highest, right?
Yes.
So if I look for traces, the pressing a pellet, compacting it with a high amount of sample really gives us the best intensity. As I said, loose powder is pretty much the same for heavy elements, but if we go to the lighter elements, we can see, right, the fusion again is blue, and the red is my loose powder. But it's not as high, and why? Because there are air pockets in there, right? So the X-rays only go in so far, and then if they don't hit that much material, they're not going to fluoresce as much. So pressing is really good, and as I said, fusion is also very good. Fusion allows you to combine different materials, right? So when we set up a calibration, we usually want to stay within the same matrix. So if you want to set up a calibration for phosphate rocks, you find different phosphate rocks and also maybe have some from your mining site and have those analyzed and mix those in. But, and then you go maybe from, I don't know, 5 to 25% for phosphate, and then have like a wider calcium range, but the rest stays the same. With fusion, the mineralogical effects are gone, and you also don't have problems with grain size. So we can actually have wide ranges for several elements. So that really helps to identify a broad variety of geological materials. So we do have customers who have, what's the word, like third-party labs to analyze samples for their customers, and they need these kind of wide calibrations.
So you had mentioned that the fusion process, you kind of can get rid of mineralogical effects. So that means that method wouldn't be necessarily appropriate if we're going to do XRD also.
Correct. That would not work.
So you'd want to do a pressed pellet in that case.
And then with the pressed pellet, that also, so that's more of an automation thing, I think. If we try to do both. If it presses without a binder, great. Then usually it can be used for both. So if one sample that's prepared and then it automatically gets put into the XRD system first and then the XRF system, or the other way around. So Angie, if you want to show it, here's kind of a setup of that, right? We have like a little conveyor belt that goes into the different systems. Maybe another one here with like a little arm.
Yeah.
Let's switch back. I only have those two pictures.
So now what about long-term?
Yeah, but if you mix in binder, then you might have to have two, right? And also sometimes you have to press so hard that it would destroy the information you're trying to get with XRD. So again, then we have to do two things.
So now we called these some of these standards and such, but what about long-term viability of them, like in terms of checking that your system is still working, or say doing a drift type correction? Would these would these samples be good for that, or do they degrade after a certain period of time?
Well, if you buy standards, they actually come with a certificate of analysis that tells you how long they're valid for. But usually NIST standards say like a year or so. If you keep them in a desiccator, if you keep them in a dry, cool place, then they are valid for a very long time. Same goes with the preparation. You can keep fused beads quite a long time, but again, store them away from humidity because they are hygroscopic and pull water. To check your calibration, it's best to set up a check standard, right? So something that you know what it is. It could be a standard, but it could also be something like a production sample. That you measure maybe daily or weekly to figure out, is it still valid? And if that starts slipping off, you look at your sample and like, oh, somebody touched it. Maybe I clean it first before I run it again. But if you notice, no, everything is fine, it should work, then you might want to drift correct, right? So drift correction is a super stable sample, usually a glass disc, not fused like this, but glass, silicon borate glass. That's probably going to be stable longer than the system. I mean, I have glass discs from an old SRS.
Oh, wow.
Yeah,
that really
those
goes
are like
back
25 years old.
All right, and you would just put that in there and maybe have the machine run it every day?
No, don't run it every day. That's a bad
Don't run it every day.
No, drift corrections you only run when they're necessary.
Okay, run when necessary.
Right? But they are tied into your calibration, and they are measured on the first day when you do the calibration, and it registers the intensities on the elements that you want to measure. And then when you notice I need to drift correct, maybe after 2-3 months, it will register the intensities again and then adjust the rest of the results.
All right, so before we get to the measurements, I think you also wanted to show us an example of an ED versus WD, so we can see what the advantage of this is.
So I'm going to show you two examples, because I think we often have this question, do I need ED, do I need WDXRF? So I'm going to
and while you're pulling
find my
that
sample
up,
first.
Just to remind everybody, ED, energy dispersive, just uses the detector to sort out the different X-rays. WD, wavelength dispersive, that's going to use a crystal, scanning that crystal over an angular range, and then that's going to sort out that fluorescence by its wavelength. All right, so I think on the screen we have...
let me see.
Oh.
We can switch it. I will just hover over this a little bit. Okay, so here we see ED and WD, and I did have to adjust the y-axis a little bit.
Okay.
So don't think you get, like this is counts per seconds per milliamp, right? This is a higher power system, so this is the best we can overlay both of these, right? Because different ways. But we can see, right, the blue is from our SI Tiger. We can see that our peaks are a lot
sharper,
more defined. But if this is my sample, and I can actually put in some lines here, and we can label them to get a little bit of an idea. So we can see there's a silver here, right? The silver is my two blinds, whereas other two blinds are there. And my system is set to find everything, so I might overshoot a little bit. But what we can see is that these peaks are wider. But if we don't have that many elements, like in this sample, it doesn't matter. Right? This could be measured with EDXRF. This is a cold sample. But if we switch to a sample, for example, the rare earth that we have here, this guy. So I have a sample that was measured on a S2 Puma, and I moved that to the system so I can show both of them. Usually we don't do that, but it's a very good thing to show the difference, right? So if I look at that, and again, we're going to switch the colors. One red, one not. So you can see there's a lot of going on here,
yes.
right? So the red is my my WDXRF, and the green is ED. And you can see, right, if I look into here, ED is not going to be able to pick up all of these peaks, right? For example, this peak, there's one large one here,
right.
but I do see two little ones here, right? So I see erbium and whatever this is, cobalt, iron, K beta, right?
Okay.
But in EDXRF, I don't see any difference.
Yeah.
Same with these two here, right? I have neodymium L beta, and I have the samarium L alpha, and here with the EDXRF, I just see one large blob. This is where you need the power of the crystals.
And even if you had, really fancy deconvolution software, that green one, you would not be able to see a lot of those features.
No, you would not.
So
there are ways of measuring the total rare earth content.
Yep.
That's a really cool thing. You can use the Compton peak for that, and then measure the K lines. There are some good papers out there from the USGS, US Geological Survey.
Yeah.
But if you want to identify each different element, you really need to have a large floor standing WDXRF system.
All right. So, and that's also probably something good for people to keep in mind if you say you don't have a machine yet or that. If you're sending samples out to a lab, be aware. What are they doing? ED, WD?
Correct.
Because you could try to regress something out of there, but it's not going to be the same. Right. So we had said all along we're going to see this thing in action, right?
That's right.
Make sure it's a real machine, not just like a picture that we put there.
Right. So let's show my screen again. So this is the loader of the system. We can actually see all the samples that I ran here. I'm going to remove this one. And we're going to run the sample again.
So now this is what's also shown on the little screen there.
That's right.
On the front
actually,
panel.
Here we can see all the samples that are loaded onto here.
All right. So that is kind of like what we're seeing virtually.
Yep.
And then for everybody out there, I can also see the same screen on that little screen that's integrated, the operator screen.
That has a touch screen.
Okay.
Touch screen is not necessary, but if you have a lot of people who are operators, not necessarily your lab manager, then this is really helpful because you just push a button and you're done. So this is my demo system. It does have quite a few options here. Quant Express, button. Quant Express is our standardless software, so the template for it. So I'm going to just call it rare earth sample. We want to evaluate it as oxides. It's prepared with 1 gram binder and 7 grams of sample, and I can make adjustments here.
Okay.
Right? This is all down the line. The diameter that I want to measure is 34 millimeter, right? That's the aperture of the sample cup, but the sample itself is 4 centimeters wide. And then I can measure this in vacuum, and I'm going to use the really, really fast measurement because I think it's really impressive how fast this goes. So we're going to put this over here, and then we're going to start it. I mean, this is really self-explanatory. And so what we're going to see is, hopefully, I mean, this is a little farther away, but you will see that the grabber in the back is going to go to the front to pick up the sample that I just defined. There you can see it. Right? And if I open this to show it better, it's going to stop because there's a safety switch to not hurt yourself if you are moving
Protect
your hands.
the operator.
Yeah,
there
in between while it's running something. However, I can open it while there's X-rays on, right?
Okay, because there's a little door that closes.
Yes. So now while we keep this is for the impatient people, because usually, right, if we run XRF measurements and we do these routine analysis, I want to know exactly what's in it, how much with a calibration. This is not so interesting. Okay. But the live spectrum of something like that is really nice, and you can see how fast it is.
Yeah, that is.
I love how fast this is and how precise the peaks are, right? This means at each position, the detector is going to dwell like, I don't know, tenth or less of a second.
Yeah, but you can, but still the signal to noise.
Yeah, it's pretty good.
Is quite amazing here. So how much power is in this one that we're looking at?
That one's a 1 kilowatt system.
Really?
Yeah.
And it can be that fast?
Yes.
Wow. Wow. So I can just imagine, because what does this one go up to? Like the highest?
4 kilowatt.
4.
Yep.
So it could be 4 times faster even.
Yes. If you wanted to.
Wow. So now, I saw you making all these settings and stuff like that. Is it every time somebody wants to measure it, they have to set those, or do you have it like where you can make a button out of that, so an operator just walks up,
You can make a button out of it, and if we do have a custom calibration, I'm going to show you an example, then most of this is already fixed, right? Because you set up a calibration saying, I'm going to prepare my samples every single time like this, so I don't need to make adjustments to the preparation, and I'm going to measure every time like this, and it's going to be in vacuum, so for that, it's always the same. So if I want to show you an application, it's already open, right? Then you measure your samples against the intent. You measure your samples against the concentration, and then you can plot the intensity, and then you get these like really nice curves. And when I get an unknown, it's measured, it registers, I don't know, an intensity up here, compares it to my calibration curve, and it knows, hey, I have 80% calcium oxide in there. Right? And this is an example of a fused bead calibration. So we can see quite, I don't know if you can see that, but it goes from 0 to 90% for several elements, right? We have 0 to 15% potassium, 0 to over 50% sulfate, phosphorus goes up to 7, silicon oxide 0 to 100%, aluminum 0 to 80%. That's why you use fused beads, right? Because you can mix several different matrices because it's all a glass.
All right. And I hear the machine moving in the background. Does that mean it's done already?
Yes, it is done.
Oh, wow.
So this is a good example of showing you the difference between running it with the best detection and running it really, really fast. I still have the other one selected. No, that would have been too easy. Where did it go? Here, found it. We found it. No problem. Okay. So if we look at that sample, or if we look at this, we can see it twice measured the same thing, right? But if we zoom in here, we can see, maybe let's zoom in here, we can see that there's a difference in terms of noise. So we can see the red one.
Yes.
The red one has a lot less noise. That one was measured dwelling a lot longer per point. That one took 18 minutes to run.
Okay.
Right? The other one took 2 minutes to run.
So the blue one is the one we kind of just took.
Yeah.
The red one you took before.
Yes. And that one took like 18, 20 minutes. So if I get samples into my lab and I don't know what they are, usually I do run them, sometimes even just as a powder, against our standardless analysis, and then we evaluate it and look at are all the elements that the customers say are in there, and are there any surprise elements that they didn't tell us about?
And then you might also want to adjust what crystal, or is it like, you have all the experience, so you would know this right away, but do you kind of like play with a different crystal?
Not with the standardless program that's kind of set up already.
That one is set up.
But for my custom calibrations, yes, it does make sense. So there are these, industry-wide, there are 3 crystals, maybe 4, that span like the whole periodic table. But you can add additional crystals, like for example the LftL220 that has better resolution for transition metals. Or you can add the germanium crystal that gives you higher resolution and higher intensity for the elements that fluoresce, where sulfur, chlorine, and potassium are. Phosphorus, sorry. Yeah.
All right, so and these are the crystals that are doing that Bragg diffraction.
Correct. So
how many do you stick in this one?
This one has 8 slots for 8.
Wow.
But to give you an example of what difference the crystal makes, I do have an example of LftL200 versus LftL220. Again, this is that very convoluted rare earth sample, right? And so we can see in red we're going to do the LftL200, and in blue we have the LftL220. And we do see, right, it does a better job at differentiating between these peaks here.
Yeah.
And this is done with a 0.23 degree collimators. We do have finer collimators too, so we could like make this resolution better, but then the intensity goes down, right? So it's always a calculation of how long can you measure, how precise does your sample need to be measured, all of these different things. And those are also the things that our developers put into the standardless program. How precise does it need to be? I mean, this program measures anything from oil to rare earth to cements to like iron, steel. Right. So it can't be as precise as a custom calibration, but it's really good.
So now with this calibration, there's like a kit, right, that you can get?
Yes.
From us?
The one that I showed earlier, where I showed the calibration curves, that's GEO-QUANT Basic. So that measures Now you got me.
It measures
It measures
kind of all
like
the
14
standard
elements
stuff.
or more, maybe 17.
Yeah.
We could look it up and count them.
Sure.
But it measures a certain amount of elements that are the most important elements in geological materials. There's also GEO-QUANT Advanced that adds a few more elements. And we do have something that's called GEO-QUANT Trace that, and the two that I mentioned first, they are fused beads, and then GEO-QUANT Trace, for example, measures as pressed pellets, but it has very good a very good trace analysis for rare earths, for precious metals, things like that, where you can do contamination or like just figure out what's underlying in your samples. Because there are mining sites, for example, that look for iron ores, but then their waste material, if it's red mud, might have a lot of rare earths in it. So it might be interesting to reprocess this, given the state that we are in, where rare earths become more and more interesting.
So, okay. So, and I apologize out there to any of my Bruker colleagues for being ignorant of how this works, because I'm going to ask you some questions about this. Like, so you get this kit, or you buy the kit with the machine.
Yes.
Now, so you get a bunch of powders in the kit, is that right? Now, do they measure that at the factory before they send the machine out, or like does somebody come on site and then measure those, or does a customer measure? How does it work? I buy the kit,
so
the GEO-QUANT with my machine.
If you have the kit, GEO-QUANT Basic, you get standards.
Okay.
Those are either NIST certified or other certified reference materials.
You get a bunch of
these,
vials.
but instead of buying each one of them for somewhere between $400 and $1,500, you just get
the whole thing, everything you need.
Yes. And then you get a manual, an installation manual that shows you how you have to prepare your sample, because you want to do it at your site. You want to have your preparation equipment preparing the standards, because your preparation equipment is also going to prepare your unknowns. And usually you get this while during the purchase discussions when you order the system, and then somebody on site during the installation will also install this. There are some that are pre-installed at the factory, like GEO-QUANT Trace, that's transferred, and it will just be on your system, and then you will have a acceptance test for that.
Okay.
But if you, for example, you have GEO-QUANT Basic and you decide, well, maybe I want GEO-QUANT Advanced, or you are a cement company that adds not mining, but adds to it to take in kind of geological materials. You can buy this later, and then you can either have somebody come on site, or we can even help you install this remotely.
All right, so if somebody's kind of getting into this, into XRF and stuff, it's a way of kind of us helping to transfer that knowledge over and make sure you're doing it right, you're getting the right results, and things like that. Okay.
Because you don't, see, these are very powerful, so you want to make sure that you have the option to use all the power. With a handheld that often comes pre-calibrated, but it only does one job, or maybe two, right? And it also is not as precise.
So now, there are a lot of options that I heard about. I mean, I've heard about collimators, I've heard about spot sizes, I've heard about crystals, I've heard about powers. If somebody was wanting to get into this, they can send samples here though, right? Because I know you have a whole lab full of this.
Yes, I also have a whole lab full of samples that are here that need to be run.
Okay.
But yes, we understand that making the decision between an S2 Puma and an S8 Tiger is, like, budget-wise very large, and you don't want to buy something that you haven't tested. So we do proof of principle measurements. We also, if you, for example, replace an older system or a different system, or you want to go from ICP to this, we take standards and we can set up a calibration as well.
All right, so you try during that process, just find the right parts, the right setup for it.
Yes.
And then when a system is purchased, then it'll go through the whole calibration and things like that. And in addition to doing like sample report stuff, people can come here, see it in action, or you also do like virtual demo stuff.
We do virtual demo stuff just like your colleagues do. Right, we put the cameras up. Usually we have measured samples before, so we kind of do a hybrid where we go through the report, and then we also show the camera, kind of like we're doing here, showing how it works, so that you see it live in action. Sometimes things don't work, so you also can see how we can take care of it right away. And we do invite our service people who are in-house as well to sometimes do a little bit of the service part as well. So I have taken off the side of a system during a demo, because that's interesting to the people who want to buy this.
Yeah, I mean, that's an important thing. I mean, don't be afraid when you're buying something like this. You're making an investment to, really ask every question you have. Like I said here, I'm asking Julia some questions. So, feel free to do that type of stuff. And I would encourage you, if you're not just Bruker, but if you're going to any vendor, make sure you're doing that and feel transparent and feel good about it, because you're going to have a long-term relationship. I mean, these are not machines that you buy for using it once. This is something that's going to be running.
Yes.
Right?
Yes.
So, especially mining.
Yes. Yes, I mean, a mining site needs to be running quite a long time to be to make sense to get the money back, right? And that's also another thing, right? These have really high uptime.
Yeah.
We make sure that we have sample care. We make sure that we have maintenance contracts. We have people in-house to take your calls. We have people for service and applications. So we want to make sure that you get the best out of your system.
Yeah. And the Tiger, I mean, it's just I know it's out there. It's all over the place.
Yes.
There's so many of these things out in the field. So.
Yes, it is. Do you want to see how good the Standardless program is?
Let's do it.
Yeah, sure. So let's look at the sample that I just evaluated, that I just ran, but we'll take the better measurement that took a little longer. Let me take my...
All right. And while Julia is bringing this up, if anybody has questions, you can go ahead and type them into YouTube. We'll get to them at the end. If you're running out of time, I normally shoot for half an hour, but if it's really interesting, we're going to keep going. Type them in, we'll answer them. You can come back, watch it later, or you can always type them in. There was the email address, live.events@bruker.com. Send them in, and we can get to them. We will post this just like we do all of our Live from the Labs. So I know how it was prepared. I can look up the LOI. Let's just assume I could have done this. And I know that silicon is my matrix, right? So I'm going to set this as the matrix. So this is my result. I haven't really weeded through all the elements, but what we can see is, right, it comes up with silicon at 67%, and here we have 66.9. It comes up with calcium, well, let's do potassium, 5.5, and the potassium here is 5.5. Those are not the interesting ones in there, right? We want to look at what does the cerium do, or what does the lanthanum do, 0.256, 0.23, so we're pretty close for not having set up a whole calibration, right? Neodymium 0.515, neodymium here, that one's a little off, 0.4. What else do we have? Maybe erbium 0.2. I have to find the erbium here. 0.175, so 0.2. So it's really close. Yeah.
I mean, I'm always impressed how good this is.
All right, and that would be Standardless, you said.
Yeah,
so
that's right. You didn't buy any standards. You didn't waste. No, I don't say waste. That was a wrong thing. Don't quote me on that. You didn't spend several hours setting up a calibration. It would be a waste if it was the wrong calibration. Right. So you just put it in, and you know what's in it.
All right. I think that's all the measurements?
Yes, I think that's it.
All right, so we do have some questions.
Took you really long.
That's all right. We do have some questions, and so we will get to those, and then also we have some that came in before. So we have one question from Farmer, and that question is, can one arrange an on-site demonstration of your portable XRFs?
That I don't want to reply to yes, because I do not represent the portable division.
What about like the bench tops?
Well, if you send them out, they don't get better, right?
Yeah.
It's a big system with an X-ray tube. It's better if you guys come here, or sometimes we do have friendly customers in the field who would help. Mm-hmm. But with the I think with the handhelds, because they can be shipped out, there's a very high probability. I would suggest you contact us, and we transfer your call to the person who would be the sales rep in your area.
All right. Next question from Moises. If I have a method that measures 10 elements, but for a particular group of samples I only need to analyze 5 elements, do I need a new calibration curve?
No. Do you want me to elaborate?
Yeah.
No, you don't need more. You can actually have master methods and then sub-methods, right?
Yeah.
Where you say, I only want to measure, you have 10 elements, and then you just say, I don't want to measure these 5, and you just don't measure them.
Yep.
You can also have something like a quick and dirty method, right? So you have one that takes 10 minutes, and then you have one where you only count like half the time, and then it takes 5 minutes.
All right. So, but measuring a subset of what you have there, that's just fine.
Yep.
All right. Another question from Farmer. When and why would one go from ICP to XRF?
That's something that, so our arguments are it's faster, you don't have any acids, you
Yeah.
don't need to have highly trained operators. If you measure majors, it's much better because you don't have to make sure that it dilutes. It's very instant. If you want to measure sub ppm levels of something, stay with ICP.
All right.
But it's really something you need to figure out what are the elements you want to measure, what are the ranges, and yes, again, XRF is also much faster.
Yeah.
Preparation is faster, and measurement time is pretty fast too.
All right, from Andre. For analysis of liquid samples where the matrix such as soil, sludge, alloys have been digested with HNO3, HCl, can it be done with liquid cups or by depositing a volume on a filter paper?
You can do both. If you want to do something like that, if you put it on a filter paper, the Standardless program might have a little bit of a problem because it's not homogeneous, right? Because you have a filter and then there is your material in it, but you can keep it in the liquid cup. Maybe you might want to dilute it and weaken the acidity, but there are good pages of the providers or the suppliers for these liquid cups and the thin films that tell you which thin films withstand which liquids.
Yeah.
And yes, you can put those in there.
Yeah. And then Prasant, we're not going to answer that one, but the question basically is, what's the better XRF, us or a competitor?
Us.
Yeah.
Always us. I mean, what kind of question is that?
Well, and these are the types of questions we do sometimes address here on Live from the Lab. That's what this show is about.
Yeah.
Really, though, send out a sample.
Yes.
Get to know the company and get to know what their service is like, get to know what working with them is like, get to know the machine, how it works for your operation. That's the best encouragement I can give, certainly.
I would agree. My colleagues and I really strive to be very honest about our machines, right? Because I think they're good. And if something doesn't work so well, or if something is not the way I would set it up, I really want to address that, right? For example, I actually don't want to use fudge factors. There is a way of doing it, but I think that's not the right way. If you need a fudge factor, something is wrong with your setup.
Right,
right. So that's something that we do not promote. Or, I don't know, something that I hear every now and then is people saying, oh, we have full fundamental parameters. Everybody has fundamental parameters. Yeah, it has been around for I don't know how many years. All computers can do fundamental parameters or variable alphas, calculations of standardless samples. That's not a standout feature.
Yeah. So I mean, call us up. Arrange a demo or see us at a show, and talk to everybody. And like I said, go find the one that you're comfortable with, that you like the instrument, that it's working best for you. And of course, we're always going to say it's a Bruker, but find the one that's best for you. All right, we do have some questions, and we'll kind of bounce between the ones that are live and this. So from Grace, what's the length of analysis and how many samples a day?
So that depends on what system you have, how many elements, what the precision is, right? You just saw one took 2 minutes, right? On average, I would say between custom calibration, standardless, it's somewhere between 4 to 20 minutes. That's where the majority of our measurements land. With like the Gaussian peak, probably around the 5 to 10 minutes.
All right. So, but you're never really measuring things for like half a day or anything?
No.
Okay. Next one from Phoebe. What are the ranges that can be measured?
Ranges in terms of concentrations. So we can go ppm level to 100%.
Okay.
Ranges in terms of elements. Boron is the lightest. Actually, we also have a beryllium crystal, but it's not coming into, I don't have a lot of requests for it.
Sure.
But boron is usually the lightest that we measure, and then all the way up to uranium.
All right. From Michael, probably in batteries, because can you measure lithium?
Unfortunately not.
All right.
But what we can do is, you saw that Compton peak that was very high with the fused beads. So there are ways of setting up something to figure out how light the matrix is. It's still something that we are also in our research labs and our application scientists look into. But lithium by itself, no commercial XRF system will measure that.
All right, and that's also where, no technique is going to answer every question.
That's right.
And that's where it's great to combine these things. So you can use, say, XRF and XRD, and then from that you can regress out a lot of things. All right, so from Jane, how do the samples need to be prepared? We talked about that a little bit. So we had pour the powder in the cup, we had pressed pellet, and then we had the fused.
It depends also on what you want to see, right?
Yeah.
One thing that's important is it repeatable, especially for your routine samples?
Yeah. And then the last one from Jack, why can I not just use a handheld? Well, we talked about that a little bit.
You can use a handheld, but it depends on what you want to see, right?
Yep.
I'm saying it depends all the time, I know. But yes, if you do exploration, or if you also at a scrap metal place or something like that, handheld is fine. If you want to figure out how much rare earth, or if you want to maybe look at the concentrates and the tailings of a metal ore site, you need one of these, or at least an EDXRF benchtop system. Yeah,
and sometimes it's a combination of techniques. Maybe you have a handheld to walk out there and do some quick analysis, but then you grab samples, bring it back, get that more thorough analysis.
Yeah.
All right, and from Hussein, any test results showing repeatability?
Yes, haha, I do have one. I mean, that's not really a repeatability test, but I think it's a very good visual.
Yeah.
If you contact us, or you can also, on the website, you can download some of our applications reports, especially like the ones for cement, where repeatability is very important. But let me show you, I did measure a sample 10 times on the ED and 10 times on the WDXRF system. And just to show you, right, so this is WD, this is ED. I'm just going to plot it both in there. It is a phosphate rock. And unfortunately, again, it's going to pick all the colors. But if I zoom in here, right, you can see this was the same sample measured 10 times on WD and on ED, and you see how well they overlay.
Yes.
Right? It's really hard to see the differences. So if I try to find one color that makes it stay out a little, that one didn't do it. Let's try another one. Sometimes it works, sometimes it doesn't. Right, so if I zoom out and go maybe into a different one, I really like how you can see how you cannot differentiate between the different ones, right? This one here, the finer peak, that's WDXRF. This one here is EDXRF.
Okay.
And I mean, yeah, I think our precision is outstanding. As I said, up to 0.05% relative. At that point, you start getting into the era of the system itself. And then with EDXRF, usually not as good, but 0.1% is achievable relative.
Now, this was the same sample prep that was already prepped, and then you ran it over and over.
Yes, it's this one.
So how does the repeatability change for a regular person if you actually are re-prepping a sample? Or if if I took this and I make 5 samples out of this?
So as we talked about earlier, right, if I just make powders, it depends on if I shake it down, something like that. If I press them, it gets better if you have no binder, because you don't have dual weighting error, right? Yeah. So then it's not machine error, it's more of a preparation error.
Yes. And
that can be avoided if you automate it. But automation is an additional investment, so is that necessary? I don't know.
Right.
But yes, there are ASTM methods. So for example, for cement, C114 definitely tests how good your preparation is, right? So you have to pass that to be accredited for your cement plant.
Yeah, I mean, and that's the same with XRD too. We find is that the machine, the repeatability of measurement, if you measure the same thing over and over again, you're always going to get the same result, but it's that prep that really you have to take care of and get that right. All right.
And I want to say about this, your system does not decide from one day to another to drop intensities or to do something else. It's usually have something.
Yeah. So if something funny happens, maybe measure the standard sample.
Yeah. Just
check it. And don't necessarily put the drift in, and then all of a sudden if the drift drops by 50%,
that's not a good thing.
Yeah. Okay. So from Moises, what are the quality or verification controls that the machine has, or what should I consider?
So our systems all come with a check sample, and by our I mean Bruker AXS.
Okay.
So the Tiger, the Puma, and the Jaguar have their own check sample that checks the machine.
Okay.
It's called the quality check or the SA check, in this case. And then it also has a check for the Standardless program. And then for your custom calibrations, I would always make sure you have some kind of check sample that you use to make sure your calibration is working correctly.
Okay. How often should somebody measure that?
So we recommend to run the SA check or the system check once a week.
Okay. So from Farmer, for the handheld XRF, does it go from boron to uranium-2, or is it sodium to uranium? Now, Julia is not an expert on handhelds. Maybe you happen to know.
No, it doesn't.
Okay. So send that question into go on our website down to the handheld area. And
even sodium and magnesium, because they're very light, are tough for handhelds.
Yeah, I know some of them have special attachments and things like that for going lower.
Yes, and you can do a purge with helium, and then there's some that you can put upside down, but then it's not handheld anymore.
Right, right. It's been converted. All right, and then one more from Moises. How does the pressure of the sample in the cup influence the final result?
Not sure I understand.
So I'm guessing either
How
there's
it is
two bits.
pushed
One,
down?
yeah. Or do you ever like put a gas in this?
No.
No. Okay.
No.
So you don't do that.
So the pressure in the sample chamber only. So if you want to measure a powder, and we do have sample care in there, so you actually are, unless you really know your way around and you want to make it measure in vacuum, there's no way that you as a normal operator can put a sample in there that's in a cup like that and run it in vacuum if it's a powder. Because if you put a powder in vacuum, it goes poof.
Yeah.
Right? Yeah. But you might have a liquid sample that's outgassing or volatile. So there we use atmospheric helium, which has a higher pressure than normal helium, so that the material does not leave the cup.
All right, and if we take it the other way, and maybe he was asking about the pressure when you press.
That's where the repeatability comes in, right? You want to, if you press your samples, you want to make sure that that is repeatable. So either set your press to always the same pressure, or if for the standardless methods, it doesn't make that much of a difference. But in general, you can actually make a series. So if you go from pressure, I don't know, 5 tons, 5 kpsi, 10, and so on and so forth, you will see that especially your lighter elements, actually all of the elements, will increase in intensity, and then they will peter out at a certain point.
Okay.
And then you might also have samples that shear. So some of the samples that you have, you might have to press with lower pressure than actually higher pressure, because they might not hold up.
So, and it's not just about the physical look of it, it sounds like. It's not like you can just press a series of them and say, oh, that one looks the best. You actually should take these, measure them, and see what the result looks like.
And you also, if you have one done, you should take a gloved finger and go over it. If it transfers to your hand, it might not be pressed well enough.
All right, and that is the last of our questions. So thank you, Julia, for joining us today.
That was fun.
No, it was great to learn about more XRF things, learn about the Tiger here, and actually bring it in the studio. That was cool.
I could talk about this forever.
If you want to talk about it forever, you can always reach out.
I'll come back to you for your show, and we'll do a second one.
And they can, and like I said too, if you want, you can always reach out to us and have a custom discussion kind of about this stuff. So always do that. But also thank you to everybody out there for joining and taking your time to watch us today. Until next time, though, make sure to keep your signal high and your background low.